Yeah, thank you very much, and it's a pleasure to be here today, and it's a very pleasant task and honor to speak both after Joe and in particular Thibault. And it's I have the luxury of working some years behind after Joe and Thibault, and it makes the task much easier, and it's also much easier to give the talk today after Thibault. It's like standing on the shoulders of giants. I would like to talk to you about the observational aspects of pulsar binaries and how we use them for testing theories of gravity, but also for having some astrophysical applications. But most of the talk will be about explaining how we do our observations, how we do the gravity tests, and then I come towards some astrophysical applications of pulsars. And purposely, I repeat some of the stuff that Thibault was already mentioning in passing, so this is re-emphasized. I would like to start actually a little bit further even than the discovery of the first binary. I would like to start with the discovery of pulsars themselves. It was Jocelyn Bell during her PhD thesis with Anthony Hewish that she was supposed to build this telescope that you can see her standing in front of. She was looking for interplanetary scintillation, the twinkling of quasars, which are point sources which had just been discovered a few years earlier. And her thesis was all about measuring these objects. And what she actually stumbled upon about towards the end of her thesis in summer 1967 was a periodic signal which turned out to be the first pulsar. It took a while for her to convince her supervisor that the signal is real, but in end of November 1967, as you can see on the slide, that was the first real observation of pulsars, and the paper was published at the beginning of '68, soon after. At that time, when you read the paper, it's actually not clear in the paper what the preferred model is, although they seem to favor an oscillating white dwarf because that was known at the time. But they do talk about rotating Newton stars, which had, of course, only been postulated before as one of the possible explanations. It then took until later in the year when Sterling and Reifenstein observed the Crab Nebula with the Arecibo telescope and were actually able to discover a pulsar right in the center of the Crab Nebula and identified with a mysterious source, a point source that has always been speculated to be something special because of the spectrum. And it turned out it was a pulsar, one of the very few pulsars that is also visible in the optical, not only in the radio. And then this pulsar was rotating 33 times a second and was the fastest pulsar until Joe and Russell Hulse discovered their binary pulsar, which really proved that these were rotating Newton stars because it was seen to be very fast. 33 milliseconds is too fast for white dwarf oscillation. And with time, actually, on a matter of days, you can see that the pulsar is slowing down. So it loses somehow energy, which is converted into electromagnetic energy and is taken from the rotational energy, and that's why it slows down. So, soon after this first pulsar was discovered, there was another flurry of paper that speculated what pulsars could be used for. And one very interesting one is the paper by Kip Thorne already in January 1969, who already at that time points out that it's possible if the pulsar has a companion that the system should lose energy due to gravitational wave emission, and therefore the orbit shrinks, and he even produced that formula in that paper. And that was already in January 1969. But it took then a few years further until Joe and Russell discovered indeed the first binary pulsar, and you have seen these pictures before. The curve on the right-hand side shows you the variation of the pulse period, or here expressed in relative velocity towards the line of sight, and it clearly shows the system is a binary and it has a high eccentricity, otherwise it would be more sinusoidal. And then, of course, we also heard there was this announcement during the Texas Symposium in Munich, and shortly later this paper, and this was indeed the first evidence for gravitational waves, which earned them the Nobel Prize a few years later. My first contact with the Hulse-Taylor pulsar, looking back in hindsight, was actually reading a German issue of Scientific American, which translated that article by Joel Weisberg, Joe and Fowler into German. I was at high school at the time, and little did I know that somewhat later I'll be standing here talking about that discovery. Interestingly, in the same issue, there was also an article about the first gravitational lens, which was discovered in the radio survey at the Jodrell Bank Observatory. And it just happened that I spent 10 years of my career at Jodrell Bank, and I'm still a professor there. So kind of this was an interesting thing. Even little did I understand the significance of the Hulse-Taylor pulsar, as we call it these days, and how remarkable it is that Joe and Russell actually discovered a double Newton star as the first binary. Because as we already heard from Thibaut, there are about 3,000 to 4,000 pulsars, 10% of them in binaries, with orbital period ranging from 53 minutes to over 200 years. And these very long periods are very rare. There are only a couple of those. So we have about 80% white dwarfs. We have about 10% Newton stars as companions, with a handful of main sequence stars, and maybe one black hole. And I come back to that towards the end of my talk. And there's a unique triple system, which also features quite nicely in this talk. How they are evolving from a binary system. You know, most of the stars in the Milky Way actually have a binary companion. And this is shown in this diagram, which goes back to all of the theories that Ed van den Heuvel, Thomas Tauris, and others have produced over the years. Here's a nice picture of that by Huan-Chen Hu and Paulo Freire in a recent review. We always start off with a massive binary. The more massive star, of course, evolves faster. It goes supernova, produces a Newton star. Very often a supernova explosion is sufficient to disrupt the system, and so pulsar, newborn pulsar, and the companion star are just flying apart, and we have an isolated pulsar, which is as the majority of pulsars, as you have seen. But if the system survives, then the companion star may evolve, and then it depends how much mass this companion has. A very massive companion will evolve fast, and in an accretion phase, passing matter as well as angular momentum to the Newton star. That period will be short for a more massive companion star, and will be quite short for quite long for a less massive star. If it's a massive companion, it may also go supernova, and again you have the same thing. Either the system disrupts, which is most likely, then you have two Newton stars born but flying apart, or if the system survives, you have a chance of having a double Newton star system. Sometimes they also become black holes in mergers later on. This is the same so-called PP dot diagram that Thibaut already showed. Just to give you a feeling for how we also can calculate numbers like age, magnetic fields, and energy loss. But the main message is that in this sort of garden variety, these are the young pulsars, and down here, these are the pulsars which we call recycled, because they were actually dead before they stopped radio emitting, because a pulsar moves from this area, crosses a so-called death line. The condition for radio emission ceases to exist. But if it gets angular momentum, it moves back into the other direction, crosses the death line again, and the pulsar, the Newton star may reappear as a so-called millisecond pulsar. And again, if the transfer of matter, angular momentum, takes long, they end up here, and the remnant will be just the white dwarf interior of the heavy companion. Or if you have a supernova explosion and double Newton star exists, you'll find those systems here, and this is shown in this diagram, where everything in red is a white dwarf pulsar system, in the blue and violet dot is a double Newton star system. The experiment that we then actually do is called pulsar timing. Conceptually, it's a rather simple experiment. You find your favorite pulsar in a binary system. The light propagates through the interstellar medium. It actually interacts with the interstellar medium. You already heard Joe and Thibaut talking about dispersion, so higher frequency actually propagates faster than lower radio frequency emission. Eventually, all frequencies arrive at our telescopes. We use our local atomic clock to time tag the arrival times of the pulsars. This is it by itself synchronized to a common time standard. And then you do some data analysis. You have some timing model, I explain it in a second. And out comes a gravity test, equation of state information, and so on. So that's as simple as it is. Of course, in practice, it is slightly more involved. But one thing is really important to take home, and Thibault made that point already, so it's really important to confirm this. We're not just measuring Doppler variations, we actually count the rotation of the Newton star. So again, to go to your telescope, and very often actually the pulsar is much weaker than the noise in your system, so you have to fold, as we call it, with the appropriate period to increase signal to noise and reduce the noise around it. And then you measure a so-called time of arrival. Then you know some information about how the pulsar rotates, where it's on the sky. So you feed that into a so-called timing model, which can predict the arrival times into the future. You go back to your telescope sometime later, at the beginning, a few hours, few days, weeks, and then the more accurate you become, the more the smaller the uncertainty gets. You can do it over years and decades if you want to. Then you go back to the telescope, you repeat that measurement, and you compare the measured arrival time with the expected arrival time, and we call that a residual. And you see some of the residuals here plotted as a function of time for the double pulsar, which I will mention later. For the most precise pulsars, the timing precision is such that the RMS of the residuals is 100 nanoseconds or less. That's a big achievement or improvement over the last 10 years or so. But the important point is, again, that we count every single rotation between the first observation and the next observation. And it doesn't matter how many billion times the pulsar has rotated. I can go back to the telescope. If it's a good timer, I can tell you plus or minus 0 how many rotations the pulsar has done. And this is indeed about 1 million times more precise as we were just taking Doppler measurements. How precise is shown on this slide. This is just some example. Oops, it doesn't show on this slide. Oh, there we go. It shows a number of measurements that we have made. The usual common practice in pulsar astronomy is we write out the measurement, and the uncertainty that is shown in the bracket is the uncertainty in the last digit or last 2 digits, depending on how much. So for instance, the first pulsar there on this list there has a rotational period of 2.947108069160717 plus or minus 3 attoseconds. So that's the precision that we can achieve with that method of pulsar timing. And there are some other quantities on that list that I will or will not be able to talk about. But let me point out that, for instance, when we do our measurement, if we do this time transfer that Thibault was talking about, we basically transfer our time of arrival at the telescope to hypothetical arrival time at the solar system barycenter. And that means, in order to do that properly, we need to know where all the masses in the solar system are, in particular, of course, the giant planets and the location. But we also are sensitive to actually the mass of Sirius, and we can turn it around. You can tell what would cause a signal over the orbital period of Sirius, and that you can then use to constrain the mass of Sirius. And we can do this, as you can see, to a precision of about 10%. I'll talk about later about gravitational wave detection, where we also have a nice precision. So much about pulsar timing, how it works. I'd like to give you some examples. And again, this is the important techniques. This is now basically at the heart of our gravity test, is what Thibault and others have developed after discovery of the Hulse-Taylor pulsar. Again, we look at these post-Keplerian parameters, which, as he explained, are theory-independent analog to the PPN formalism. It's a phenomenological description of what the orbit does, so that we can describe the times of arrival. And you can measure this, and then, for instance, this is the gravitational wave damping in GR. As you can see, the structure is the same for all post-Keplerian parameters. It depends on the Keplerian parameters here, the orbital period and the eccentricity, plus a combination of the masses of the pulsar and its companion, which you don't know a priori. So if you have measured the PB dot, you see that the orbit is shrinking. You have measured PB, you have measured the eccentricity. What you don't know are the two masses, and therefore you have this line in this, what we call a mass-mass diagram. The shape of this line is given by your theory of gravity, and the location, the scale, is given by your measured Keplerian parameters. Siebold already mentioned, if you have two post-Keplerian parameters measured, the intersection point, if you believe in your theory of gravity, usually of course we assume GR, that gives you a nice mass measurement of a Newton star. And here's a glimpse of all the mass measurements that we have done so far. And you see some of them have quite large error bars, but the majority have error bars that are even too small to be shown on this scale. And I'll come back to this plot later. If you have three or more post-Keplerian parameters, you expect them to all intersect in a single point. If your theory of gravity is a good description of your data, that gives you this n-2 independent test of GR. In this case, the theory would have passed. In this case, the theory would have failed. And you have seen this plot already. This is for the Hulse-Taylor pulsar in the most recent incarnation of Joel Weisberg's work. Here's another plot, this time with the Shapiro delay added. So the Shapiro delay has now been detected to some weak significance in that system. And I just wanted to show you here, this is the formula that Siebold already showed you in some other version. Here's the range and shape that he explained. I just wanted to show you how the plot looks like for an inclination angle that is only 50 degrees and something that's more edge on. The more edge on the system is, the peak here the curve gets, and the amplitude gives you the mass of the companion. Siebold already pointed out that in '91, Joe and Siebold scratched their hair why the observed PB dot in the Hulse-Taylor pulsar was deviating from the expected GR value, and you also explained that the main contribution is actually coming from relative acceleration. There is a real acceleration due to the movement of the pulsar in the galactic potential, as he already explained. There's also a kind of apparent secular acceleration that comes from a proper motion of the pulsar as it moves on the sky. And if you then basically this apparent distance becomes larger, and also the pulse arrives later with a nonlinear trend, and that's why we have the contribution also to the observed PB dot. So both of them are sort of adding to the observed value. You have to subtract them to get the intrinsic one before you can do your test of GR. If you turn this around and actually assume GR is correct, you can actually use that axis to measure the distance of the pulsar, because the relative motion term here, the Shklovsky term, depends on the distance of the pulsar. And if you do this, this is the axis curve as a function of distance. This is the best distance Joel has produced some years ago. Actually, that would have been the best distance here. This is too far out in the galaxy, so we believe that the Hulse-Taylor pulsar is probably about 7 kiloparsec away from Earth. That is quite far away. And of course, after the Hulse-Taylor pulsar was discovered, many more than 300 binaries were discovered. And I would like to talk to you a little bit about this object here. If you see this from the top, which you can see is much closer to the sun, and actually it's less than a kiloparsec away, whereas the Hulse-Taylor pulsar is quite far away in the other side, on the other quadrant. And so knowing the galactic potential here to sufficient accuracy is actually limiting our current precision of the test that we can apply to the Hulse-Taylor pulsar, whereas here, sort of in a local neighborhood, we know the gravitational potential rather well. And there's another interesting a circumstance I will show you in one of the next slides, which makes this test much more precise. What we discovered in 2003 using the Parkes telescope in Australia was a system that does indeed consist of two active radio pulsars. So our Hulse pulsar had one active pulsar and an unseen Newton star. Here we have a 23 millisecond pulsar and a 2.8 second pulsar, whereas the 23 millisecond pulsar is recycled, it's old, and the 2.8 second pulsar is young. They both have orbital velocities of about 300 kilometers a second. The orbit is very compact, it's only 3 light seconds across. And we see the system actually from, as I will start this again, we see the system actually from almost completely edge on. From a measurement, I'll show you later how we do this, the tilt to perfect alignment is just 0.65 degrees. And the system allows us to measure lots of different effects to very high precision. I'll just go through some of them and then move on to the next source. First of all, we can do very precise astrometry. We're not only doing timing, but we can actually do also very long baseline interferometry. And in particular, the latter gives us a parallax measurement, which gives us a distance of 735 plus minus 60 parsec. This is a similar plot as I was showing you before for the Hulse pulsar. Here I have separated, however, the contribution from the Shklovsky term, which is this one, and the galactic acceleration, which is this one. This is again the axis, here is 0, and you can see that for the measured distance, actually these contributions are almost equal in magnitude, but of opposite side. So very fortunately, they almost cancel each other, which makes this effect, this extra access to the intrinsic value even smaller. The system also almost stands still in the Milky Way. We measured a transverse velocity of only 11.5 kilometers a second. We have done a lot of measurements. In an average, we have an observation every 10 minutes that produced almost 1 million TOAs. And these TOA measurements produce very precise binary parameters, which then encode the gravity test that I will just show you very briefly. I would like to point out already now that the most precise parameter that we have measured is indeed the periastron advance, which is very large. It's even 4 times larger than the periastron advance in the Hulse pulsar. It's almost 17 degrees per year. And that means that since we discovered this pulsar in 2003, it has almost exactly done a full revolution in space. So that is much, much larger than the effect we can see in the solar system. And the precision of that measurement is already so precise that we should be able to measure any 2pn contribution at a level of 35 sigma. And that becomes important when I speak about applying this to get the moment of inertia of the Newton star. Just to prove you that it is a double pulsar, this is an observation we did in 2004. What you can see here, straighten out, we've taken out the Doppler variation, is the emission of the slow pulsar. So these are different pulses. And on top, superimposed, you see these faint lines. These are the pulses of the fast rotating 22 millisecond pulsar. So if you would calculate the separation, you can get to 22 millisecond. Actually, it's 11 millisecond because it has 2 components, but that's a detail. But you can see is actually in your beam, you have 2 pulsars pointing towards your telescope. In fact, we just didn't discover this second pulsation right away, because it turns out that the second pulsar, we call it very cleverly B, is only visible in certain parts of the orbit very strongly. That puzzled us, but the model that we came up with, and which seems to fit the observations very well, is that this millisecond pulsar rotates so fast, it emits this very strong, powerful wind of electromagnetic radiation and particles, and that blows away half of the magnetosphere of pulsar B. And it's more like a cometary tail, what is left of the magnetosphere. And only when we see the sort of the wind-absorbed sides, we can see the radio emission. Nevertheless, having at least some detections across the orbit allows us to measure the orbit independently for B and A, and that allows us to point out that the ratio of the masses is the inverse ratio of the orbits, and that gives you this ratio, mass ratio of 1.0714. And to at least the first post-Newtonian order, this is independent of your theory of gravity. So this is a unique new constraint that we don't have in any other binary pulsar. Not then, not yet, not now. I'll come back to that. Of course, the gravitational wave emission is also visible in this system. Here, this leads to shrinkage of the orbit of 7 millimeter a day, or in terms of change in orbital period, this is 107,820 plus minus 7 picosecond a day. That is not much. However, in 85 million years, the two neutron stars will collide and will probably produce a large amount of gravitational wave emission, probably a black hole, and that kind of emission would have been detectable then by LIGO. Particularly, it's very close by. Tibor already pointed out that this is the most precise confirmation of the GR quadrupole formula. We tend to write 95% confidence limits here, so 2 sigma. And so this is why the factor of 2 sometimes in the error bar that you will see. Here, this is the same plot as you will have seen for the Hulse-Taylor pulsar. You can see the excellent cadence, the frequency of observations that we have. And again, the error bars are too small to be seen, and the red line is not a fit to the data, but the prediction of general relativity, which is like pearls on the strings. In fact, our precision is so high that we need now to take into account that the system is losing mass because it emits electromagnetic radiation, E equals mc squared. This is 8.4 million tons a second, or 3.2 times 10 to the minus 21 of the mass of the pulsar per second. That is not a lot, even though 8.5 million tons sounds a lot, but you can see from the mass of the Newton star that it's quite a tiny fraction, but it's a third of our error budget, so we need to take that into account. It is also a much more precise confirmation of the GR quadrupole formula than what's possible with gravitational wave detectors. We can test the dipolar contribution, we can test the quadrupolar distribution 3 orders of magnitude better than what LIGO can do and will do for the foreseeable future. But of course, they test dynamical space-times, so then they soon take over. But in principle, the combination of both is a very hard constraint to anything that should deviate from the prediction of general relativity. Light propagation in strong gravitational fields is something that gravitational wave colleagues cannot do at all. So it's very interesting to look at that in some more detail. Here, because we see the orbit more or less completely edge on. The Shapiro delay peak that I showed you is very peaky, almost as peaky as it gets. It has an amplitude of 120 microseconds when the pulsars are lined up towards Earth. And then the distance is only 10,600 kilometers of the photons to pass the surface of the foreground pulsar. And that takes a bit longer because space-time is curved, and that leads to the delay that we see. And again, if you compare the observed and measured, the expected shape and range, you can see the beautiful confirmation that Tibor was already pointing out earlier. You can convert that into measurement of the orbital inclination angle, and it's 89.35 plus minus 0.5 degrees. And that's why we know it's more or less edged on. There's one effect which is quite nice because it's a lot of fun. We didn't expect that to be seeing this. If you take the GR prediction of the curve as I used before, the formula that you've seen to first post-Newtonian order, then you can actually, and you subtract that, you can see this very distinct shape. And I was puzzled by that when I saw this the first time. So I took this plot and went to Norbert Wex, who's just a few doors down the line. And Norbert has been insightful in so many different things. And so he just looked at that and said, oh yeah, you discovered light bending or a higher order Shapiro delay. What does it mean? So First of all, there are two contributions to this. One is retardation, because the orbit is so compact that when pulsar A emits a photon, and this goes across the orbit within its 3 light seconds, within that time, B has actually moved, and the 1pn description of Shapiro delay doesn't take that into account, and so the curve actually shifts a little bit to one side. But that's not the only effect. The other effect is that we also have aberrational and light bending effects. What happens is that the pulsar A has to shoot the photons at some later phase in order to compensate the light bending near pulsar B in order to reach us here on Earth at the bottom of this diagram. Whereas just after superior conjunction, of course, it has to shoot in the opposite direction, so a little bit early compared to the usual emission of photon time, and so to compensate the bending in the other direction. And that makes this distinct feature here. So here the pulse is emitted somewhat later, and here it's emitted somewhat earlier. Otherwise, you wouldn't be able to see the pulse on Earth. And that, of course, depending on the signature here, that gives you the direction of the spin of the pulsar relative to the total angular momentum vector. So that's a very nice way actually confirming that pulsars are rotating Newton stars, because if they wouldn't be rotating but oscillating, this effect wouldn't be there. And in fact, the light bending gives another 600 kilometers to the 10,600 kilometers that I was mentioning before. And again, it's in very nice agreement to the expectations in GR. Now, I will make the point later on that we got some very nice new telescopes in the near future. In fact, one that we have already is, apart from FAST in China, is the Meerkat telescope in the southern hemisphere, which is the core of the square kilometer array. And we have used Meerkat for a couple of years now, since it was inaugurated, to observe the double pulsar. And it's a 64-meter telescope, but it has a collecting area of nearly 120 meters equivalent dish. And it's in the southern hemisphere, which is the right hemisphere to observe pulsars, because there's lots of them. A student of mine, Huan-Chen Hu, she's now a postdoc, she has used Meerkat in her thesis to basically do in 3 years of her thesis what took us 16 years and 6 telescopes to do before. So Meerkat is really a rather sensitive telescope, and this is the plot just based on Meerkat data, 3 years compared to 16 years of data with 6 telescopes across the world. And she also confirmed the Shapiro delay and improved the whole light propagation by a factor of 1.65 in a very short time. This is an effect which is very peculiar. You may not be aware of this, but if you go to Thibaut's and Natalie's paper, you'll find out this is the other parameter delta theta that he was showing on one of the slides. Effectively, you have this other eccentricity, and that means that your orbit is not a pure ellipse, but it's actually deformed, looks a bit like an egg or a potato. But this is vastly exaggerated here. But for the first time, we can constrain this parameter. Joel in the Hulse pulsar also get a 2 sigma constraint. We have shown here that it actually correlates with this gravitational redshift parameter gamma. And if you wouldn't know that the correlation exists, and if you would take this parameter to be set 0, you would actually get a deviation from GR at about a 2 sigma level. But in fact, it's because we see this deformation of the orbit and the correlation of the parameter with gamma in this case. You have seen this diagram before. This is the mass diagram if you have everything put together. You have also seen the masses. And here is just a table from the paper that we produced with the tests of GR, the various tests that Thibaut was mentioning. Let me point out that we have this 5 post-Keplerian test. We have next to leading order detections of the signal propagation for the first time, the most precise strong field test of GR. We need to take the mass loss into account. And Meerkat, and this was really astonishing because it beats all our expectations, the most optimistic estimates. But Meerkat improves the timing by a factor of 2 to 3, and so this is the reason why Huan-Chen was able to do this improvement in a rather short time scale. And we start to probe the moment of inertia on the equation of state of Newton stars with this system. And for that, I need to explain you a little bit of what frame dragging does in our measurements. So frame dragging is, of course, if space-time is taken around by the rotating mass. And in pulsars, it can have two effects. It can lead to wobble of the orbit, which is very difficult for the system because it's nearly edge-on. So sine I derivative of that is cosine, so you don't see much when it's 90 degrees. But there's another contribution, which is to the observed periaston advance. So what I've done here, we zoom into this very intersection point. This is a very blown up version. We just show you the gamma parameter, the Shapiro delay parameter. You see the relative accuracy. You see for the first time that is actually strips of plus minus 1 sigma. And you see the width of the PB dot measurement, and you see this really tiny, small, super precise periaston advance. Now, frame dragging has a contribution, as I'll show you on the next slide, to the observed value of the periaston advance. And if you ignore frame dragging, it will be here, but with some assumed equation of state, in this plot here, you can show that it shifts quite dramatically away from this intersection point that we would have otherwise defined here. So if you were to measure the real intersection point and the true location of your omega dot, you can turn this around and infer the equation of state of your Newton star. And that also goes back to some work that he did with Gerhard Schäfer, where they could show that there is at the second post-Newtonian level a contribution of the lens steering of the relativistic spin-orbit coupling of pulsar A to the observed value of omega dot. So this is the observed value, and if you actually calculate it, then you get some number which depends on the geometry, which we know very well. But here is the moment of inertia of the Newton star. Now, why would you be interested in that? Because the moment of inertia encodes the equation of state and tells you how dense you can pack super dense matter, and that's something nuclear physicists are extremely keen to know. We have not been able to make the PB dot measurement small enough to isolate this true separation, but what we can do, we can already put an upper limit on the radius of the Newton star. And just from pulsar timing, just from measuring when the pulsars arrive here in our telescope on Earth, we can tell you the Newton star is less than 22 kilometers across at a 90% confidence limit. And Huan Chen has also worked on this, and she had shown in her thesis also that with Meerkat and Meerkat Plus, which is an extension you're building with just right in the Kourou, and then the SKA, we should be able to turn this into real measurement of the Newton star radius and the equation of state. Before I come back to that, when I talk about astrophysical applications. Thiebaud and Remo Ruffini were in Princeton, as we heard, in 1974, and their paper was the first one that came out before even the discovery paper was published. And they pointed out the spin precession that is called geodetic precession, or more generally speaking, in relative spin precession. This, of course, has been measured, for instance, by gravity pool B and other experiments in the solar system, but it's a weak field regime, as Thiebaud and Remo pointed out in their paper. If you do this actually with a binary system, you can test a strong field regime. And what that means, I have this animation, which is now almost 20 years old, but it's still working and hopefully demonstrating the effect. Let's concentrate just on the red sphere, which is my Newton star. Let's say that's the Hulse theta pulsar. We zoom into that and we add some vectors which designate rotation axis, magnetic field axis, then let the pulsar rotate around this rotation axis, and then we let the pulsar precess around the angular momentum vector, which is green. And so you can see that the beam is actually pointing in vastly different directions on the sky. So the pulsar may or may not be visible depending on where you are to observe it. Eventually it will point in our direction, like here. You can see the pulsar, and then eventually it will also disappear again from the sky. So people were looking for this effect. In particular, they were looking for the effect that the pulse shape should be changing. And so we're not using pulsar timing here. We're actually using information how the pulse looks like. In the nice, beautiful paper by Thibault and Joe in '92, they call this pulse structure information. That is exactly what it is. So let's say these are two different phases of precession. Then we saw at one phase we cut the emission beam with our line of sight here. You would see a wide pulse, and a different phase of the precession you will see a narrow pulse. So you would really expect a change in pulse width as a function of time. So when Joe and his group, in particular Joe Weisberg, Roger Romani, looked at this, there was no variation seen at the time. It was Arecibo data, and you can see this is the pulse shape. It has two components, and they have almost equal amplitude. But they did see, however, with time that one component, this becomes weaker with time, and if you plot this, you get this almost linear trend. But they didn't see the variation in the width. I happened to observe this pulsar with Effelsberg, actually with our 100-meter telescope to take over the Arecibo timing observations while Arecibo was doing an upgrade. And I started to see the change in pulse width quite clearly. This is a factor of 10 in collecting area. That's why these error bars are much bigger than what you can do in Arecibo. But the effect is clearly visible, and so the pulsar is undergoing geodetic precession. I had a model that, this is an animation which is also more than 20 years ago. So this is what I had predicted 23 years ago. This is I had assumed a simple cone model with some component in here. This is our line of sight, and it moves through the beam due to precession. And here I calculate the ratio between the leading and the trailing component. It goes down, but there's a time where it goes up again. This is the separation of the components, of course. If the line of sight is out, it will disappear. So I predicted at the time the pulsar will disappear around 2025, so next year. I'll show you, if you stay tuned, what we actually see. So this is a cliffhanger. So if we were to look at the double pulsar, for instance, it also geodetic precession, in fact, a factor of 4 larger than what we see in a Hulse theta pulsar. And fortunately, pulsar A is still visible, but pulsar B has left us temporarily. This is observation of the pulsar B as a function of modified Julian date, which is time. And you can see, if you were able to calculate this in your head, in 2008, it disappeared. So at the moment, the double pulsar is no double pulsar anymore, at least for us here on Earth. For someone else, it is. But we believe it should come back anytime now, or depending on the latest model, it may still take a while. However, we can still see B in the effect it has on A. And that's a really nice effect that René Breton was doing in his PhD thesis with Vicky Caspi in McGill at the time. So what happens is that because we see the system nearly edge on, we have this magnetosphere which looks like a donut because it's filled with plasma, and the donut rotates. Remember maybe the animation from the very beginning. And this plasma is optically thick for the radiation that comes from the background pulsar. So if you watch the pulsar in the background, the pulsar B, A is in the background, B is in the foreground, you will see how the light of B is now, the magnetosphere of B is now blocking the light of A. So it starts to disappear. It's blocked, visible, blocked, visible, blocked, visible, blocked, visible. You see this at the dips of the emission that you see in the bottom plot. Blocked, visible, blocked, visible, blocked, visible. So it's actually half a rotation of B, but then suddenly it's blocked for the full rotation of B. So it's blocked, visible, blocked, blocked, visible, blocked, blocked, visible. So that pattern changes from half rotation of B between the peaks to full rotation of B. And that pattern depends very sensitively on the orientation of your spin axis of B. But remember, it's precessing. So this changes as a function of time. You can see this here in the two observations, December 2003, shortly after we discovered this. Here you can see the emission here in this otherwise eclipse area. And later, a few years later, there's no emission here at all. And so what René did, he took all the observations that we have gathered and did a global model with only 4 unknowns, which are basically the orientation of the spin axis, the precession rate, and the size of the magnetosphere. And you can see here, as a function of time, how the eclipse pattern changes. And by comparing what we observe in that simple model, he was able to derive the precession rate of the system with a rate of 4.77 degrees plus minus 0.6. This is a 13% test, in which was the best test at the time. We have used Meerkat to continue these observations. Actually, again, we have not combined GBT, and this was mostly GBT data and Meerkat data. This is just based on Meerkat data on its own. This looks a bit blurred, but you can see how beautiful signal-to-noise ratio you have here compared. Let me go back to this data here. So you see the improvement in the sensitivity of the telescope. It's really breathtaking. And so Markus Lower, PhD student at Swinburne, now a postdoc, he has done, this is the precession phase of the orientation. This is the orientation of the phase of the spin axis. You can fit a straight line and you improve on the rate. And the test is also in agreement with GR, and you has improved this test by a factor of 2 to 6.5%. And this is shrinking this line, which you saw in a previous mass plot, by a factor of 2. And there will be more improvement possible once we combine this with our GBT data. So again, it shows how beautiful the telescope is. The most beautiful case, the most precise test of GR in terms of spin precession comes from this pulsar 1906-0746. Thibault also mentioned it. And it's beautiful because of 3 different ways. First of all, it's the most precise test. It is also something that is verifying a model that was predicted in 1969, immediately after the discovery of pulsars, which we did not confirm up to now. And it allows us to learn something about radio emission also. For that, I need to explain a little bit. So this pulsar is actually seen, we see both poles. It's oriented in orthogonal mode, as we say. You have the north pole pointing towards you and the south pole in one rotation. So let's say this is the north pole and this is the south pole. So think about the cone. Let's assume it's a cone, which points to its direction, and this is your line of sight. And in this case, the north pole, our line of sight, cuts below the magnetic pole. You see this looks like a wheel. These are actually the planes of the feed line, because they also think about it as a dipole. These are your feed lines looking right onto the pole. Oops. And then this is your line of sight. If you then calculate what the polarization degree is of your emission, because the plasma is like pearls on the strings going along this feed line, so you get polarization direction here, 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 and here, and here. If you plot then, or you measure the direction of the E vector, polarization vector, you get that S-like shape. That curve is steeper, you closer to the magnetic axis, and flatter the further you are away. And then on the southern pole, you do the opposite, because you're on the other side of the magnetic pole. And so you get the opposite slope, okay? So on this side, you get this slope. On that side, you get this slope. And this is what we observe. This is the pulse. This is on north pole, south pole. The red is the linear polarization fraction. So it's very high. 90 is almost 100%. And there's some circular polarization as well. So then Gregory Devine did this very nice observation, well, a very long time span, again, almost 20 years. And you can see how our line of sight moves out of the north pole and into the south pole. And you see how the pulse profile changes. So suddenly this becomes weaker and this becomes much stronger. And then suddenly this will eventually disappear, the north pole, because we're running out of the beam and we're running into the beam here on the south pole. This becomes the strongest part. So you can put this all together, you piece this together, and you get tomography of the pulsar beam for the first time. And you can also see that the polarization, if you just concentrate on the south pole here, this is the position vector, the polarization angle as a function of time. And you can see that it's changing from a slope like this to a slope like this, which means we have crossed the magnetic pole. So we know for the first time, that this position angle of the polarization is indeed giving you the geometry of the system, something that was proposed by Randa Krishna and Cook in 1969. We're only able to confirm now. Anyway, so this gives you the geometry just because of this very, very precisely, and that gives you this beautiful few percent test of GR, which is again in agreement. The other reason why it's so beautiful is because for instance, there are some plasma theoreticians who said that if you have a 90-degree orthogonal rotator, then there should be some absence of the emission just above the magnetic pole. And believe me, that's exactly what we see. For the moment we cross the magnetic pole, pulsar B was temporarily invisible. The south pole was temporarily not visible, and we see exactly what is proposed here. And we can also actually measure the altitude where the emission comes from. So it's a beautiful laboratory also for emission physics of pulsars. But I come back to the cliffhanger. This is the Hulse-Taylor pulsar as we have continued to observe it. You can see here in a cartoon strip fashion how the profile changes. So it's actually still a little bit narrowing, but not as much as before. And the amplitude is actually not going further. The amplitude ratio is not going down further, but almost turns over. And this is an observation with Meerkat, so it shows that we all see the same thing. This is the polarization, the same trick as we did for the previous pulsar. This may be confusing. Different colors are different epochs, but you can see it's getting slightly flatter, which means we're moving out of the beam as we should. And if you look at the amplitude ratio, compare this with the animation that I did more than 25 years ago, just look at the ratio plot in the top left, you'll see we are more or less here at this point. A few years late, which means it's not quite right what I predicted at the time, but the spin alignment angle is the same as before, but possibly the pulsar will not disappear 2025, but will continue to be visible for some time, and we're just in the process of updating the modeling to see when it actually disappears, if it appears at all. Spin precession or geodetic precession has now become a routine observation. Whenever we expect spin precession to be detectable, which means we need a misalignment between the pulsar spin and the total angular momentum vector, just like here. So this is the orbital vector. This is the pulsar. Whenever we have a misalignment, we should expect precession. And all for these red cases here, actually the A pulsars are black. All with the red cases we have seen precession as observed. For most of them we cannot do a quantitative test because it is taking too long to see profile changes, or the modeling is too complicated. But even in cases where we didn't expect it, this is a new pulsar which observed it fast, we did find geodetic precision. I'll say a few words about testing the foundation of GR alternative theories of gravity. Thibaut already gave an excellent coverage of that, so I just concentrate mostly on a triple system that we heard about some time already. So this is all about the universality of free fall. If you drop some test masses at a hammer or a feather, if there's no air resistance, they should all fall the same. And I really like this video. This is an experiment they actually did in Apollo 17 on the moon. So he has a hammer and a feather in his hand, and there's some sound which I don't transmit now, but he will see at some point he will drop this and you will see that the feather and the hammer, this is a high precision experiment obviously, but they fall and hit the surface at the same time. There's much more precise measurements with microscope, 10 to the minus 14 and minus 15. Thibaut already pointed that out. And you can do this also with lunar laser ranging. You basically see if the moon and the Earth, this is the Nordtvedt effect in experiment, whether the moon and the Earth, the different self-gravity fall in the same way in the gravitational field of the sun, and you get this very precise number. If you divide this in terms of self-energy, the test is 0.04%. And you do this with lunar laser ranging. You shoot a laser from an observatory here. It's reflected by this laser reflector that the Apollo astronauts left on the moon surface. If you ever ask, did they ever land on the moon? Yes, they did. They left these laser reflectors. And so by measuring the light travel time, they measure the distance very precisely. And that's how they can see if Earth and Moon fall in the same way. And indeed, to this limit, they do. Tibor was already mentioning that if you do this experiment with a pulsar white dwarf system, you have two different bodies and they're falling in the gravitational potential of the Milky Way. You get this induced eccentricity in the binary orbit. And the best limit on a given pulsar is on 1713 plus 0747 by Zhu et al. But that effect is actually quite small because the acceleration in the Milky Way is actually not that great, even though it does disturb, as you have seen, our binary pulsar test to some extent. And there comes the triple system. So this triple system is really unique because here we have a pulsar in about a day orbit around the white dwarf. And there's a second white dwarf further out in about a year's orbit. And so the pulsar and the white dwarf now fall in the gravitational potential towards the other white dwarf. And that acceleration is about 7 orders of magnitude larger than the acceleration that we have in the Milky Way. And in fact, it's of the same size or same order of magnitude as the Earth and Moon in this in the solar gravitational field. And we have 2 self-gravitating bodies. And so this is the real test in a strong field regime. And you basically do the same way as we do lunar laser ranging, but in a strong field equivalent. And this is a test that was first done by Archibald with a team that discovered the triple system that was discovered by the GBT, and they get this beautiful stringent limit on the violation of the university of free fall. And if you divide this by the self-energy, this test is actually better than lunar laser ranging. Guillemot Visson used the Nancy telescope, not so far away from here, with very high cadence daily observations data set, a beautiful data set. And together we produced this test. We actually did an analysis which is less prone to systematics that was done by an Archibald and collaborators, and we get a similar precise limit, but as we believe better than less prone to systematics. And Guillaume is writing another paper where he is arguing that there is some residual structure in the data which may suggest that there's actually a planet in the system also. You have seen this plot already. So this is where the triple system really comes in producing these limits. Everything below a line is allowed, everything above a line is forbidden. As Tibor already pointed out, the triple system really rules out most of the solar system, much better than solar system constraints, and the double pulsar cuts off here on this side. If you were to have a system that is consistent with other tests, but not the double pulsar, this is how the mass plot looks like. And you can see the intersection point here is all over the place, and that's why this is ruled out. And this is, I wanted to show, this is a plot that Norbert Wex produced not long ago. Again, you see the triple system, our favorite pulsars, but here is also 2 lines in there which shows what's possible with the 3rd generation of gravitational wave detectors. Here, as an example, the Einstein telescope. So even with the Einstein telescope, these limits will never be better than what the pulsar experiments already produce today. A lot of more can be tested. I really also want to refer to the same kind of reviews that were already mentioned. You can test local Lorentz invariance, existence of gravitational dipole radiation, already pointed out, variation of gravitation constant, and the graviton mass base bound from binary pulsars. There's this review by Paolo and Norbert has this beautiful table with the references. So if you want to learn more about this, just go to the review and click on the corresponding reference. The ultimate system, and I should come closely to the end, would be if you find a pulsar around a black hole system. because then we can do all the beautiful things we can already do with a Newton star companion, but now with a black hole. Also, the black hole doesn't have hair, so scalar fields shouldn't be there. And so you will have an extreme mass dipole, and you will be very sensitive to the very alternative theories that Thibault has been describing. Also, you will be able to measure the spin and the quadrupole moment of the black hole to some good precision, in particular if you happen to find one that orbits the Sagittarius A star black hole. And with that, we will be able to describe the black hole Sagittarius A star inside out. We can test the no-hair theorem and the cosmic change conjecture, which means there should be an upper limit to the spin of the black hole. Otherwise, we may see the singularity. And so this is something we're trying. We're searching for pulsars in the galactic center to find such a pulsar for a long, long time. In fact, that was a topic of my PhD thesis, and I hope I still find one before I retire. However, there is one pulsar system that may already be a pulsar black hole system, not a million solar mass black hole, but something more modest, a stellar black hole. We published this earlier this year. And this is a pulsar we discovered with the Meerkat telescope. It's in a globular cluster. And from the mass function and the measured total mass from the orbital precession, we know that the most likely value for the pulsar is 1.53 solar mass. That's not too super exciting. But the companion is about 2.35 solar mass. That is much heavier, more massive than we would expect from a Newton star. It is pretty light for a black hole, but possible. So it falls what our gravitational wave colleagues have coined the mass gap. We don't know what is the largest mass of a Newton star or what is the lightest mass of a black hole. But that system is right there where we expected to see. In fact, it's similar to some systems that were observed by LIGO, where they can't tell whether they saw a black hole or Newton star event. And we have space telescope data. We have a very precise location. You can see this here. There's nothing there, so it's not a normal star. If it is a Newton star, it's likely to break the equation of states that many people have proposed, or it's a lightest black hole, and that would be the first be of its kind. And we hope that we measure some frame dragging effects in the future, which will allow us possibly to tell between the two alternatives. And that brings me finally to the astrophysical applications. I already showed this plot in small. These are the mass measurements that we have available. You can find this on Paulo's website at our institute. The most interesting ends are the ones which are the most massive Newton stars, but also which are the lightest ones. The most massive Newton stars may not be supported by certain equation of state, whereas the lightest one we have difficulties to form astrophysically. So that binary evolution plot I showed you before may not work for the most light. So there is a evolutionary lower limit to what we expect the Newton star mass can be. And finally, we can also use masses not only from relativistic effects, but we can also see what the optical companion does. And so we get the radial velocity from the optical companion, compare this with the radial velocity from the pulsar, combine the two, and we have done this in this measurement here. This was the first Newton star where we sort of gone through the two solar mass boundary. And this is just an alternative. You don't need always relativistic effects to measure the mass of a Newton star. This gives you this plot here where we plot radius versus mass. And everything that you can see on plot here is a proposed equation of state, which describes how dense you can squeeze matter. This comes from nuclear physicists usually. But you can see that some of these sort of turn over at a certain mass. So if you find a Newton star that is more massive than the turning point here, that equation of state needs to be ruled out because they cannot explain the Newton stars that we measure here. And here we have the two solar mass companion, and another two solar mass companion was discovered with the GBT. Some of them may actually not be so massive because they accrete matter, because they were born massive. And there was also a hint that we see bimodal distribution of masses in Newton stars, but with our last increase in mass measurements, we don't believe that anymore, but that's something of current understanding. Just want to show this slide, which is made by Anna Watts, a colleague in Amsterdam, which shows you basically that by combining radio observation with X-ray data, in this case data from the NASA instrument on the International Space Station, they look at the hot surface of millisecond pulsars. They have hot spots because the plasma that creates the radio emission is created in some pair cascades. So you produce positron and electrons. Some of them are accelerated upwards, but some are accelerated downwards, depending on the charge, and hit the surface and heat the area around the magnetic pole. And so if you know how big that is, you can model this. And if you know what the mass is, you can convert this into another constraint in your mass radius plot just by combination of radio and X-ray data. And so these are beautiful measurements that were done by Anna and her team. And again, the idea is to shrink these shapes to points where we can really try to measure what is the true equation of state. And think about then the moment of inertia of the double pulsar, which will also be just a point here, hopefully, in this diagram. Two more examples and then I'm done. Binary interstellar medium. This is a nice and beautiful observation again with Meerkat of the double pulsar. What you see here is the intensity as a function of frequency and time. We call this the dynamic spectrum. So everything which has a bright thing, the pulsar is strong. Everything that's dark, the pulsar is weak. And so this is orbital phase, and this is for various frequencies. This is about 800 megahertz, this is about 1400 megahertz, and this is about 2300 megahertz. And what happens is, we call it scintillation. The pulsar is weak and strong. This is the twinkling of stars at night sky. You have the scintillation in the atmosphere. Here we have the scintillation in the interstellar medium. And because in a binary system the pulsar moves backwards and forwards in its orbit, the relative velocity changes as a function of orbital phase. And that induces the changes in the pattern in the dynamic spectrum that we see. Now you can model this, in particular here for the double pulsar, and you can look at where the pulsar is located. If you look at the map, radio map, this is the so-called Gum Nebula, probably the remnant of a supernova explosions, which maybe created this star here, which is shown here. It's just located at the edge, and we never quite knew whether the pulsar is in front or behind the Gum Nebula. Was Jacob, this is a paper submitted, could show that Earth is here, this is the Gum Nebula, and the pulsar is here. And we can identify two locations of some interstellar medium which interferes with our emission. And in this case, we can actually measure the distance, the orbital inclination, and the properties of interstellar medium along the way from these simple observations. And that's possible because the binary modulates the relative speed towards the Earth and the interstellar medium. And the very last example was also mentioned before, but it's worth mentioning yet again, which is that with pulsars, not necessarily binaries, but lots of them are in binaries, we have built a galaxy-sized gravitational wave detector. The idea is that if you have a source of gravitational waves, like supermassive black hole binaries, when galaxies are merging, they produce gravitational waves that are propagating through the universe and eventually hit our pulsar Earth system. And indeed, the space-time is squeezed and stretched, and that leads to variation in the arrival time of the pulsars. And we should be able to see this. Now, this experiment is ongoing in various parts of the world. We have the North American, the European, the South African, the Indian, the Australian, Chinese experiment. I hope eventually we will truly work together as the International Pulsar Timing Array, but the results that we showed last summer was a coordinated effort, but we all analyzed our data on our own. And all of us saw basically the same thing, which is the so-called Hellings and Downs curve, which is a correlation of the arrival time as a function of angular separation on the sky. Explaining this may take more than a minute, so these pulsars here on zero are in the same direction on the sky. They come early, late, early, late. Pulsars that are orthogonal on the sky are anti-correlated because of the quadrupolar nature of the gravitational wave. And pulsars in opposite directions are again correlated, and that gives a so-called Hellings and Downs curve after the two colleagues who calculated that for the first time in the 80s. And you can see that our measurements, so you measure the arrival times, you correlate them with pulsar pairs, you can see that the correlation curve is indeed as expected from GR and the existence of a gravitational wave background. We can measure the spectral index of that signal, which is somewhat lower or larger, depending on what the minus sign is taken into account, of what you would expect from a supermassive black hole binary population in a galaxy. But actually, this is for circular orbits. If the orbits are slightly eccentric, you can explain that. All the pulsar timing wave experiments measure the same thing. And the level of the amplitude is about the order of 10 to the minus 15, which means we have a precision of 30 meters of space-time variation over 1 light year. That's the precision we're achieving at the moment. The European pulsar timing array actually uses 6 telescopes. We're collaborating with our Indians, and we have the longest data set. This point is mostly done by efforts, but also non-say. This is uniquely available for the European data. And if you take that data point into account, the spectral index is actually spot on where you would expect it. The MeerKAT results have been submitted, and they're very consistent with all the other arrays. So I would say there is sufficient evidence that we have detected the gravitational wave background, and whether it's supermassive massive binary black holes or something more exotic will need to be found out. And that brings me to the outlook. We continue to find binary pulsars. These are just the parabolas for the orbital decay for a number of sources. These are the ones we talked about mostly today, 1913 and the double pulsar. But there was a nice receiver discovery, a very beautiful system, even in periostin advance, larger than that of the double pulsar. And then it's the most luminous in terms of gravitational wave luminosity that we discovered with a telescope at Parkes, one of our PhD students. And again, so this just shows the more you look, the more you find. There are lots more discoveries with FAST, and lots of more discoveries with MeerKAT, in particular soon the SKA. I won't go into detail, but we have converted MeerKAT into a very efficient pulsar search machine, and that, for instance, led to the pulsar black hole system that we saw today. And that is a summary plot where we try to compare the different experiments, not only pulsars, but gravitational waves, solar system effects, the S-stars in the center of the galaxy, EHT. And so yes, as Siebert already pointed out, the space-time curvatures that we're probing are orders of magnitude more precise than those at the event horizon of the supermassive black holes. And that is the conclusion. Pulsars provide the most precise and often unique test of strongly self-gravitating bodies. They produce, as we have heard, tight constraints on alternative theories, which need to be passed binary pulsar tests. The measurements are usually clean and precise because we're dealing with almost ideal test masses, and all of them have confirmed GR so far. And we probe with a regime or parameter space or effects that are usually not accessible by other methods. And therefore, I truly believe that even in the future, even in the era of gravitational wave detectors and generation detectors and other experiments, binary pulsars will still be competitive in terms of test and will be needed to test certain aspects of the theory. It's really a shame that Einstein didn't see the discovery of pulsars, or in fact most of radio astronomy. But my thanks really goes to Jocelyn for finding pulsars in the first place, but also people like Joe, Russell, Thibaut, Natalie, Joel, Jill, hopefully online, and others for showing how to use them. I should also mention Norbert and Paolo and many more from my group. So there's much more to come, and I'll stop here. Thank you very much.